to make 32 different modified strains in parallel. And what's mapped here is the frequency of modifications at each of those sites. The key thing being is that while there's a lot of different variation of performance from site to site, all of those 314 changes were ones that the organism was willing to let us make, that it was content with, if you will, and didn't die on it. Next slide, please. And almost finished. And so this schematic from the paper that I think Neil mentioned that just came out last month schematizes the two major processes that we use. The first one, essentially on the left half, taking the starting genome of 4.6 million base pairs, marking out the 32 segments we wanted to modify, making those different changes in 32 different strains, but then we have to combine all of those strains together to make one big modified genome. And so the pairwise hierarchy that we're going through as you go from left to right is a process called CAGE, Conjugation-Assisted Genome Engineering, pioneered by my colleague Farron Isaac, who was in the church group at the time. He's now at Yale with his own lab. And here, like a Final Four tournament, the pairs of modified chromosomes get stitched together so that increasingly we have more cells that contain more and more of the modifications that we're interested in. And where we are now, shown with the dotted line, is going from the 1/4 modified genomes to the half modified genome. And we're very close now to having the fully modified genome that would be the first organism with a genetic code that's been engineered throughout its entire genome this way. Next slide, please.
2 minutes.
2 minutes.
Great. Oh, perfect. Well, let me say my thanks again to Joe Jacobson, who has been my advisor for the bulk of this project. I most recently, last month, moved to a different part of MIT Lincoln Lab. And particularly 3 students in our group that I've worked closely with, Bram Sterling, Chris Emig, and Sam Huang, and Bram especially, who has put a ton of work in this project over the years. In George Church's lab, I mentioned Farron Isaac, Harris Huang, who got his PhD finished up last year and is now a fellow at Harvard's Wyss Institute. Marc Lajoie, a grad student with George, and also especially Xuguang Zhang. I'm broadcasting from his turf at MIT right now, who's been an excellent collaborator over the last 10 years. Thank you very much for your attention.
Molecular biology is the real role model for digital fabrication, where the code becomes the thing and the thing becomes the code. That's where the technology is developing. This is the frontier. And so what Pete just showed is with roughly, it's a little bit more work, but with roughly the ease with which in your word processor you do cut, copy, delete. Somebody's waving at me.
I can hear you.
Your mic isn't on.
My mic is not on. I'm wearing a mic, but I'm not going to take the time. I'll talk. Is this on? Good. Can it go down a little? Okay. Good. Thank you for waving at me. So with the agility, roughly, with which you do cut, copy, paste, and delete in a word processor, you edit a genome. And Pete showed making life with genes other than the one, a genetic code other than the one that evolution gave us. So before we go on, any questions or comments for Pete about editing the genome?
I was a little confused. I'm not a geneticist, I have no background. So when you switch the base pairs from TCAG to UCAG, are UNT just, in the second slide, the base pairs stop being TCAG. The combinations are all with U.
Yeah, no, I'll repeat the questions to save time, but tell me the question.
The slide that shows the combinations of base pairs
Yeah.
shows them as UCAG.
Yes.
As the letters for the codons, and the introductory slide shows TCAG.
Pete, just the question is, what are the letters of the codons? Just recap the symbols of the code.
I'm sorry, Neil, could you do that one more time? I'm having a little interference.
Sure. Just recap what are the symbols in the genetic code, and then what is the change you made?
So so we want the genetic code slide up? Yeah, it's okay. The genetic code, recap the genetic code. I apologize for the difficulty hearing you. The genetic code itself is the 64 three-letter words with 3 DNA letter words corresponding to the 20 amino acids that are our protein building blocks. In addition, 3 out of those 64 codons are used for stop signals, which signify the end of for every protein, there's a signal that says this is the beginning of the protein and this is the end of the protein. There's the start codon is typically ATG, seen on the lower left, MET. And there's a special version we use for the start of the gene. There are 3 different ways to signify the end of the gene, the stop codon. And what we did in looking for opportunities in the genome that we thought were achievable, we chose the codon which is least used entirely throughout the E. coli genome. So there's about 4,400 protein encoding genes. All of them have a stop codon, but only a little more than 300 of them use the TAG stop codon circled there. And that's the one that we have reassigned at all 314 instances to the codon just above it, the TAA stop codon.
Okay, that's a great summary. And in turn, so many things radiate out from this. One of the most shocking ones for me is with these extra codons freed up, you could think about coding the construction of what weren't traditionally biological materials, growing into a very interesting kind of boundary between organic and inorganic in the future. So with that, thank you, Pete.
My pleasure.
Now, we'll introduce the audience to Megan, and Megan to the audience, and switch to, that was frontier research on rewriting the genome. The iGEM project has been doing spectacular work on making that kind of technology globally accessible. So, Megan?
Great. I get to sit up here. Perfect. So, thank you to Neil and everyone at Fab7 for inviting me to tell you about iGEM. I'm Megan Mazaraza, the Assistant Director of iGEM, and I'm excited to be able to tell you about what we do. Pete talked about these library of pieces, of parts, and iGEM is part of that. So, if you want to advance to the next slide, please. Great. So this is our group. This is what iGEM is all about. iGEM stands for the International Genetically Engineered Machine Competition, and these are our smiling students from our annual iGEM from Above photo. You can see how they're all happy faces and very excited to participate. And so iGEM, the iGEM competition, is the premier undergraduate competition in synthetic biology. And there are student teams from universities all around the world participating. They are participating from 30 different countries all around the world, and they're all working in synthetic biology with these standard parts. So what are standard parts? What is synthetic biology? We should start from the beginning, so advance to the next slide, please. And it all started with these 3 guys. So Randy Repper, Tom Knight, and Drew Endy. You can see that they are standing in a biology lab. You see the chemicals and glassware behind them, but they actually aren't biologists. They're all engineers. Randy and Tom are computer engineers, and Drew is a civil engineer. And around 2000, Tom really decided that he wanted to get into biology. So he stopped working on his computer engineering work and decided to get into biology and became essentially a grad student in biology. And he took the courses and took the exams and learned everything he could about biology, thinking that it was kind of the next frontier, if you will. And so he decided, he realized that his engineering background didn't really translate into biology as he thought it should. So he was surprised at the fact that there weren't engineering principles applied to biology. Next slide. He was used to working with this, right? He was used to being able to hook up his system to a meter and be able to get a reading that was to some level of 5 digits of accuracy, and you just hook it up and the monitor would give you some readout. And so, next slide, he expected when he encountered biology that he would be able to do this. He'd be able to hook up his cell and get that same level of accuracy for whatever testing he was doing. But instead, next slide, what he found was that biologists were using essentially Jell-O, right? So they were running DNA on gels that to him was not what he was used to in working in engineering. So he started thinking about these issues, and he found that, next slide, that as he was working in biology, he had to do 2 experiments for every 1 experiment that he wanted, right? He had to do the first experiment to create the piece of DNA that he wanted to use, and then he got to do the experiment of testing or characterizing whatever that piece of DNA was. And coming from the engineering background, this was something that he didn't understand. So he wanted to see if he could change this. And so he developed this idea of biobricks, these standardized parts, that if you look at the diagram, you can see that there are those blue and green pieces in the middle of this circular plasmid. And the idea there is that each part encodes for a certain function, so for a certain biological function, such as a ribosome binding site, a terminator, a particular function that you would be interested in, and then the outside of the parts would have a standard format. So if you think of the child toys Legos, how you can fit Legos together, and you can build any system from these Legos, and you know that they're all going to fit together. That was kind of the general idea behind biobricks. You could take these parts and make it easy to fit them together and create your systems. So, next slide. So they started thinking about these biobrick parts and how they could apply principles of engineering such as standardization, abstraction, apply these principles that they were very familiar with to biology, and they decided they wanted to answer this question. Can simple biological systems be built from standard interchangeable parts and operated in living cells, or is biology just too complex? And that's what they were hearing, right? People didn't believe that this was possible. Biology is very complex, and Tom and Randy and Drew and others set out to see if this idea of standard parts was possible. So what did they do? Next slide. They were at MIT, and they took advantage of having MIT students around, right? Yeah, the students don't know whether this is possible or not. You just give them an idea, and they'll go off, and they'll think it's exciting, and they'll work hard, and they will make you successful and prove you right. So at MIT, there's a class during January where students can take courses in any topic, and so they decided to create these synthetic biology courses. It's called IAP. And so on the left, you see the IAP class from 2003. On the right, you'll see the IAP class from 2004. And Pete is in one or both of those pictures. He's been involved in this. So what they did was the students worked away with these ideas of synthetic biology, next slide, and ideas of engineering. And you see here, this is something that engineers are very familiar with. This is a system-level diagram or device-level diagram, and you can see all the devices in their system, and you're basically demonstrating the entire system at the level of these devices. And if you look down even further, next slide, you'll see these parts that I was referring to, right? So each one of those icons is a BioBrick part, is a standard part. And so their system, the project that they were trying to make, is translated or represented by this diagram with these parts. And so the students had to think about, well, what parts do I want to put together? How am I going to make my system do what I actually want it to do? And the idea is that each one of these parts could be put together in a simple fashion. So at that point, because of this standardization, right? So at that point, you're looking at, you're paying more attention to the design of your system as opposed to the construction. The next slide. So they had so much fun during these IAP courses, and 1 month wasn't enough time for them to get as much as they wanted to do done. So they decided to expand it into a summer competition. So for the summer of 2004, they invited some friendly groups from universities around the area, and they worked away over the summer. They got some funding from the NSF. They worked with parts, and they had a great time. So this was 2004 with 5 teams. Next. 2005 with 13 teams, and this was the first international year with Cambridge, ETH Zurich, and Toronto. Next. 2006, 32 teams. Next slide. 2007 with 54 teams. Next is 2008 with 84 teams, 2009 next with 112 teams, and next is 2010 with 130 teams. So you can see that in 7 short years, we've gone from 5 teams, friendly universities, kind of competing or gathering for the summer and working on the same thing over the summer, to a competition that's 130 teams. Oh, actually, next slide. I forgot. I updated it for this year. We don't have our iGEM from above photo yet because that happens in the fall. But this year we have 165 teams from 30 countries around the world. So let's say you want to assemble a team or you want to participate in iGEM. Next slide, please. How does the iGEM competition season actually run? What do you have to do? So to begin, you have to assemble your team and register your team. So you can see here one of our smiling teams. You can see there are a lot of students. This is a student-led competition. The students come up with the project. The students do the work. They own this project, and that's what makes them come into the lab at 3 in the morning to actually work on their project. Instead of having the professor saying, this is what you need to work on, and this is the research you need to do, the students come up with the project, and then they're really excited about it. So you assemble your team, and we like to say that you should have half biologists, half not biologists, half male, half female, just a wide variety of representation on your team. And so this is during the January, February, March period. In March, you register your team, and you actually sign up for iGEM. Next slide. And at that same time, you have to start raising money because you can see the t-shirts here, right? Those are all of the team sponsors. You have to raise money to participate in iGEM. You have to pay to attend the jamborees. You have to pay to participate. But most importantly, you have to pay. Sometimes teams pay the students. Sometimes they don't. Wide variety of budgets, but teams do raise a lot of money. The average team budget is about $25,000 to $50,000 US. But there are wide range of budgets. Next slide. So then you receive this DNA distribution. And so we've talked about these standard parts. And every single iGEM team that signs up automatically gets signed up to receive this kit of parts. So there you'll see these 384 well plates. You'll see the iGEM stickers and pins because, of course, you have to have the iGEM pride, and then some other pieces that are available or that will help you in building your project. So every single team gets this kit, and it's kind of a turning point for the team in that the students think this is great. They can go that afternoon into the lab, and Pete's showing his iGEM pin, very nice. they can go that afternoon into the lab, resuspend some DNA, and just work away. And this is very different from what traditional biology researchers are used to. You're used to having to find a gene or something of interest in a paper, contacting the author, seeing if they're willing to send it to you, or even if they can find it in their freezer for them to send it to you. And here these students are, the professors never had this kit of parts. Here the students are getting 1,000 parts in the mail right there and then that they can go into the lab and use. So that's a fundamental difference in our world. Next, please. So using these, so we also have workshops where the students and the instructors learn about iGEM and synthetic biology and what they have to do, and get to know all the other people that are participating in the competition. So we build up this sense of community. Next. And so then during the summer, or I should say during May to around October, the students work at their universities over the summer. They don't all come to MIT to work. We don't have enough space for all of them. They work at their universities in the lab over the summer, however long they can work. Next. And then they come in the fall to present at what we call the Jamboree. And this is, or the Jamboree is this year, as I'll tell you about in a second. But the Jamboree is the kind of culminating event where everybody comes and presents what they've worked on, and they have a blast. They give presentations, they give posters. You can see here everybody's excited and colorful. Everybody wears team t-shirts they design. And next slide, they all compete to win awards. So there's awards for best wiki because everybody documents their project on the wiki, best part, lots of different awards. But fundamentally, everybody comes together and really enjoys the event and their experience. So what are some examples of projects that teams have done in the past? In 2007, the Berkeley team did a project that they called FactoBlood. And they took the hemoglobin system and engineered it into bacteria so that they were imagining that you could use this kind of artificial blood to then give out in times of need when there were blood shortages, because that happens very often. It's a great idea. I know they did get part of it working. They even thought about what the body would do in response to this engineered bacteria in the blood. So they thought about making sure that they wouldn't harm the person, it wouldn't be rejected by the person's immune system. So it's a really great project, and I think they're continuing to develop this. Next slide. In 2006, the Edinburgh team developed this arsenic biodetector to detect the level of arsenic in water wells, because in countries around the world, there's a problem with arsenic poisoning in the wells. So the idea is that they created this, they engineered their bacteria to detect arsenic and give off a pH change. So they would the idea was to send tubes of freeze-dried bacteria to the villagers all over the world, and they would then go to their water wells and fill it up with the water, and the next day they would be able to tell which water had the least amount of arsenic. So next slide. We had BioBeer, which is kind of a fun project from Rice University. They wanted to live as long as their friends who drank wine, so they took that component from wine and engineered it into yeast. Next is the Cambridge team, and they engineered pigmented bacteria. So you can see, next slide, that there are a lot of different projects, not just one. Next slide, please. Everybody doesn't work towards one goal. Everybody comes up with their own project. So we talked about the iGEM competition. Next, please. And new for 2011 is the high school competition. So we had five high schools from the U.S. For 2011. They competed. They had their jamboree, and everybody was amazed at what they were able to accomplish. So high school registration for 2012 will open in November of this year, and go to igem.org to find out more information about that. Next slide. I'm going to go a bit faster here because I do have a bit more I wanted to tell you. We also have, as part of our community labs, next please. Next. Yep. And there, go back please. We have labs that sign up to participate in the community in synthetic biology. And right now we have over 150 labs, and they get the same resources as the teams. They get the kit of parts, they get space on the wiki, they get access to all of these resources. Next, please. Next. There you go. This is our freezer. So we've been talking about these standard parts. We house all of them. We have over 7,500 parts available to iGEM teams and labs and high school teams. Next, please. We have our get and give philosophy. So this is how we get so many parts. There's this idea that you get the parts, you get access to the parts, and you're expected to give those parts, any parts that you make, back to the community so that so teams in subsequent years have access to more and more parts, and we just keep building up our collection. And it just keeps growing and growing, and people can have access to a lot more variety of parts. So let's see. Next, please. So if we go to...
2 minutes.
Yep. Okay, great. Why don't we just head to the last slide, please? Oh, and go back one, sorry. So there's a lot going on, right? I'm running out of time because there's so much I wanted to tell you. But the basic gist of it is that we have the iGEM competition, the collegiate division, we have the high school division now, we have labs. There are so many different ways for you to get involved and find out what synthetic biology is all about. And in particular, since Fab 7 is in Peru this year, I wanted to point out, I hope that there are a lot of local participants at the event. For 2012, we will be expanding these regions. So for 2011, we have 3 regions, the Americas, Europe, and Asia. And for 2012, we're really interested in growing. We imagine we'll grow another 25% for next year. And we're starting to think about the possibility of having a South America region. So if there's anybody who's interested in that, please let me know. Next slide, you'll see my contact information. Send me an email, megan@igem.org, and I apologize for not getting through everything I wanted to tell you, but it's very exciting, igem.org. Thank you. If you have any questions, I'd be happy to take them.
So, Pete told you about actually rewriting a new genetic code. Megan told you about designing organisms by putting together building blocks. And there's a very close connection with Fab Labs we're discussing and expect to develop. The Fab Labs go from making citywide internet to buildings down to structures with micron features. iGEM is assembling things with nanometer features. But there's a very interesting recursion. There's a barrier to entry in the lab equipment to be able to do the molecular biology, but much of that equipment you can make with the tools in a Fab Lab, things like a PCR cycler. And so we're looking at a collaborative project to use Fab Labs to make tools for iGEM labs as a direction over the coming year. So with that, any questions for Megan about iGEM as a project or designing organisms with building blocks? No questions about creating life? Give it a minute.
It's a lot to process, so visit the website.
Okay. Then with that, thank you, Megan. So next we'll introduce to the audience to Quim. Quim Quim is going to zoom out. Mute for just a minute more. Pete showed editing. Quim, can you mute just for a minute more?
I'm sorry, I cannot hear you very well.
Okay. What he's going to talk about next is not bacteria, but design. The idea is you have design tools that make things. How do you figure out what to make? Rather than saying what to make, it'd be nice to say what you want and have the design tool figure out how to make what you want. And so Quim is going to talk about design optimization. So go ahead.
So can everybody hear me? Okay, buenos días a todos. Yo no hablo mucho español, pero como soy portugués, hablo portuñol. I will continue in English because my Spanish is not that good. Okay, name is Kim Martins. I direct the Multidisciplinary Design Optimization Lab here at the University of Michigan. And I'm going to talk to you about just an introduction to the topic, assuming you don't know much about numerical optimization, which some of you might. The next slide, please. So multidisciplinary design has a strong connection to aircraft design because starting with the Wright brothers, it was really a big challenge to pull knowledge from different disciplines together. Their approach was more of a separate approach where each discipline was separated according to function, aerodynamics for lift and drag, propulsion for thrust, and structures just to hold everything together. So these things were more or less developed separately and then integrated at the end. While they were developed separately, their interactions were more or less ignored. Now, next slide, please. We have 100 years later, about 100 years. For example, here is a cutaway of an A380, a much more complex machine, as you can see. And we can no longer afford to be ignoring the interactions from the beginning. And these include interactions with economics and marketing and so on. So we really have a big challenge today in designing these complex machines. So before I go on to MDO, multidisciplinary design optimization, I would like to explain the design optimization part. So next slide, please. And namely, numerical optimization. So numerical optimization is we have a function that we wish to minimize. So typically, when we're doing design, we want to minimize or maximize some measure of performance. So for example, in a structure, it might be the structural weight, okay? But that's mathematically given as a function, and we want to minimize that by varying a set of variables. And this could be a very large set of variables that's indicated there as X. And as an example, if we want to optimize or design the aerodynamics, we would change aerodynamic shape. So changing the shape of the wings, fuselage, etc. And finally, the C there are the constraints. So the optimizer will not have complete freedom. It needs to, is subject to some constraints. So for example, if you want to minimize weight of the structure, you cannot do that to the detriment of safety. So the structure still needs to hold up. And so the stress constraints and other structural constraints cannot be violated. Next slide. So in comparing a conventional design process with the optimal design process based on numerical optimization, you can see there the conventional on the right and the optimal design process the conventional on the left and the optimal design process on the right. You more or less have the same procedure. You start with some specification. You start with a baseline design, some initial guess. But then the inner loop there is slightly different. So on the conventional process, we have some kind of numerical analysis or experiment, so a prediction of what's going to happen. And in the conventional design process, this could include some building. In the optimal design process, this analysis must be numerical, so it must be the result of some computer simulation. Then we evaluate the performance. In the optimal design process, there's a very specific way you evaluate it. This is calculating that objective that I showed in the previous slide and the constraint. Whereas in the conventional design process, this could be more informal and it could be the interaction in the group in evaluating this performance. Then, in the decision on whether the design is optimal or not, this differs from the conventional process in that you actually check for the mathematical conditions that show that this is absolutely optimal. And this is in contrast with the conventional process where you might just ask if this is good enough, if you can improve it. So it's less formal, mathematically speaking. So this is the iteration that is used in the optimal design process. Next slide, please. So I will give you a simple example here of multidisciplinary design optimization applied to a wing design problem. So in this case, we have very simple models. We have what's called an aerodynamic panel model for the wing that you see there. The structure in the middle there that's a bit darker, that's the structural model using a finite element beam analysis. And what we want to maximize here is the range of the airplane for a fixed amount of fuel. And you can see an equation there that lift and drag appear as well as weight. So it's really a multidisciplinary objective function here that takes into account both the structural weight and the drag. So on the aerodynamic side, we're going to compute a type of drag called induced drag, and we're going to be varying the twist of the wing, as well as the angle of attack. And on the structure side, we're going to size the structure so that it doesn't fail. So if we go to the next slide, you can see how important it is to consider the coupling of the two disciplines. If you click on the slide, you'll see the difference there in the displacement of the wing. This is a 77. Click forward, please. You can see how the tip of the wing moves up, indicating a very strong coupling between the aerodynamics and structures. Going on to the next slide, what you see in this flow diagram is a typical approach used in industry, which is called sequential optimization. And I'm going to show you some results comparing sequential optimization to MDO. So in sequential optimization, what you do is you would do some optimization in one discipline, so aerodynamics first, then the structures, and go back and forth, okay? If you go to the next slide, you'll see a sound MDO approach where you couple the two, but the optimizer sits on top. You're not doing sub-optimizations in a discipline. So this is a more integrative approach, a concurrent approach to design optimization. If you go to the next slide, you'll see that the result of these two. So in green, you see the sequential optimization. Okay, this is a plot in the two variables. One is the structural on the on the vertical axis, the sizing, and on the horizontal axis, you can see the aerodynamic variable. And in sequential optimization, only varying one at a time, so you see that set pattern in green. And what you see is that it converges to a result that's not optimal, whereas the blue one, which is MDO, will converge to a better result in terms of range. Okay, so that's our main motivation for doing a concurrent approach for design optimization using MDO. Next slide, please. This is just showing the lift distribution on a wing. You can see there's a vapor condensing. This is just so you can see in the next slide. You see this is the span-wise lift distribution. What you see in blue is the optimal distribution in terms of the aerodynamics. This minimizes the induced drag. But when considering everything, what you want to do is the one in red, which sacrifices some aerodynamic performance to obtain better overall performance by a reduction in wing weight. Okay? Next slide, a very quick introduction to optimization methods. Engineering intuition is still very important, but if you go to the next slide, you'll see there are gradient-free methods, and in this case, this is a problem where we're find the minimum of the contour plot, which is called the Rosenbrock function. And the next slide shows gradient-based methods. You can see the gradient-based methods as a much more direct path towards the minimum that's shown there as coordinates 1, 1. So showing the difference between gradient-based versus not gradient-based methods, you can see in this slide, next slide, how it scales with the number of design variables. And this is basically to show, click one forward please, that, click forward one slide, that basically this is a log-log plot showing that non-gradient-based methods do not scale well with the number of design variables. And typically in our problems, we want to use a large number of design variables, and therefore gradient-based methods are advised. So there are various methods for sensitivity analysis. And next slide, you can skip 2, I think. One more. Actually, one more. So a very brief introduction to various sensitivity analysis methods that can be used to compute these gradients. It is crucial that you use a method that is efficient for a large number of variables, and those last 2 that are highlighted there are advised. We're going to skip the next slide because we don't have much time left. Skip one more. One more. Transition. One more. Okay, so what I'm going to show you here briefly are some results for optimization of aircraft for minimal environmental impact. And this is using an MDO framework that includes, as you see there in the center, aerodynamics, performance, geometry, structures, weight, propulsion, and so on. So this is a truly multidisciplinary system coupled to numerical optimization. One more slide. You can see if we have single objective optimization, it makes a big difference what objective function you choose. So if you choose to minimize cost, you get the configuration on the left. The middle one is for minimizing fuel burn. For that one, I should point out that we're flying basically at 60 to 70% of the speed of current airliners. And as much as I'd like to save fuel, I would not like to fly that slow. On the right there, you see one that's minimizing a particular set of emissions that are important for local air quality in airports. Next slide. So with numerical optimization, we are able to do all these trade-offs, and you can see there that we can optimize different airplanes for different costs of fuel. The fuel is only a portion of the total cost of operation of the airplane, so varying the price will affect the design significantly, as you see there on the top. Next slide. The other data that numerical optimization and MDO can give you is a multidisciplinary trade-off. So here you can see a trade-off between emission fuels and these NOx emissions, which are related to airport air quality. And you can see that if you disregard the NOx emissions, you get that design on the upper left. So that is basically minimizing the NOx emissions with no regard to emission fuel burn. And the other extreme is on the lower right, where you see a design that minimizes fuel burn with no regard to NOx emissions. And then we have everything else in between. So this gives information to the designer in terms of what trade-off are you going to make between these two different objectives. In the end, you do just choose one design. So on the last slide here, what I'd like to show you is another application that's not aircraft related, but because it involves aerodynamics and structures, we were able to do that in our research group. And it's an application to wind turbine blade design optimization. This is the case I like because the starting point that you see there, the baseline design, is really not being designed at all. This is basically a plank and would not work as a wind turbine blade. It has no twist, it has no taper, the structure is constant thickness, so it's very inefficient. And this was done using a coupled aerodynamics and structures code, as I showed before. And we are changing the structure and we are changing the aerodynamic shape in order to maximize annual energy production for a given annual profile of the wing. So what you're going to see is an animation of the optimization in process. So it's what the optimizer is doing and all the intermediate steps towards the optimum design. And what you're going to see is the first few steps, the design varies quite a bit, and then as you progress, it's just refining, and the changes in the last part will be barely visible. So if you click ahead, you should be able to see the movie in action. So you see a lot of jumps there. And you can also see the displacement. The black line shows the undisplaced shape, and the color is the displaced one. And you can see towards the end of the movie, the changes are not perceptible as just because of the nature of the optimization algorithm. And that's all I have. I'd be happy to take any questions. Okay.
I need the microphone on. Hello? I've got it turned on here. You need to talk. Okay. Hello? This Mr.
I'll do the talk loud algorithm.
I'll do the talk loud algorithm.
So don't worry, the algorithms are not on the final exam. But what you should learn from that is the first two talks introduced design reaching these wild regimes of a new genetic code and a new organism. This is very important work on the design tools, not the drag shapes to make what you want, but you say what you want, and the design tool knows how to give you what you describe you want, not it tells you how to make it, you don't know it. It's a very important direction for the future. So questions for Quim about design optimization? Let me start with one. Talk about
the modeling.
In the optimization,
Talk about the evaluation steps.
Oh, the simulation, right?
Yeah.
Yeah.
Yeah, so one important, there are various degrees of, is there any aspect of the modeling that you're interested in? Or?
Sorry, say that again?
I was wondering if there's any aspect of the modeling that you're interested in, or should I just talk about it in general?
Just in general.
For
MDO to work. The design environment needs to talk to the model environment. And so,
right.
Two important parts to that. One is how do you build models that you believe in?
Right.
And the second is how do you build design
environments that can talk to the model environment?
Could you comment?
Right. Okay. So on the first question, it's not. I do a lot of modeling, and you really have to do a lot of validation, right? So that's a whole other field that other researchers are more involved in. So you're right that you need to be able to believe those, because otherwise the optimizer I can guarantee you that the optimizer will always exploit any weakness you have in your model and try to break it, basically. So you are right in that we do need to be able to believe in those, and for that we need validation. On the second part, how we get the modeling to talk to the optimizer, a lot of times that gets to be a pretty complicated computer science project. But in essence, what you need is an API where, and typically optimizers have an API that with callback functions, where what the modeling needs to provide is the value of the objective function and the value of the constraint. And the modeling must take as inputs the design variable. So for whatever model you have, you must set things up so that you can be able to vary the inputs and have the model automatically produce values for the objective function and the constraint. Okay? Those are the basics. Now, when you're using gradient optimization, it is also desirable to do some calculation of the gradient. Okay? But that's another story.
Okay, great. Thank you, Quim.
Thank you.
So now, if Quim can mute what I'm on. Good. Quim, can you mute, or I can mute you? Congratulations, you've graduated from the hard part of the day. But before we get to the, in a sense, easy part, I wanted you to see where you're headed, because in the future you will be able to design life. And this sort of research is what's going to give you the ability to tell the machines what you want. So it's very important to see where that's coming. We're going to end this block, which again is the hard part of the day, but with an easier part, which is once you have these resources you can design with, and these techniques, then you need to present to you something that lets you interact with the design. So we have Chris from Autodesk. Autodesk is a very interesting company that's essentially taken over much of high-end graphics and design, and have been doing very interesting work on design tools that are designed for mortals, not narrowly defined engineers. So, Chris?
All right, thanks, Neil. Buenos dias, good morning. My name is Chris Romes, and I run the engineering department for a new business unit at Autodesk that we just started this year called the Autodesk Consumer Group. And in the Consumer Group, we have a mission to unlock the creativity in everyone. So I'm going to talk a little bit, some of you probably aren't familiar with Autodesk, so I'll spend just a few minutes explaining what we do at Autodesk in terms of our products and the markets that we serve. And what I'd like to do is just play a little video here. It's not really a soundtrack, just a little bit of music. You might be able to do it. Okay. So you can see Autodesk works in a lot of different areas. We have three main divisions. We have a manufacturing division that has different types of mechanical design and engineering and simulation tools. We have an architecture, engineering, and construction division where we focus on civil engineering, infrastructure projects, building design. And then we have products for media and entertainment. So these are products like Maya and Max and Softimage, Smoke, Flame, different products that are used in Hollywood video production, TV shows, and video games. So the idea with the Autodesk Consumer Group is that we're going to take this technology that's been used for professionals in many different engineering and design disciplines and repurpose that to be used for consumers. So when we talk about repurposing the technology, there's many different criteria that we need to look at. We need to look at price, we need to look at ease of use and accessibility, making the tools less complicated, and we need to look at ways that we can help build communities around the tools that we provide, and also to provide content so that consumers can not have to start every design from the beginning, but to be able to build on other designs. So these are some of the things that we're working to do. I think we're just about done here with the video. Okay, so There's a lot of things that have, you might ask, why is Autodesk interested in consumer software and consumer products? And there's just a lot of things that are happening in the world today that are making it a lot more viable and creating the opportunity for individuals to be able to do design and to be able to do fabrication. The personalization of design is a big moving force in terms of many of these markets. And then, as those of you that are involved with Fab Lab understand very well, that the tools for doing fabrication and manufacturing are really becoming available for people, for small groups and individuals. Things that used to only be available to large manufacturing organizations because of the cost or the complexity can now be done by individuals in, with relatively low-cost machines and processes. So within the consumer group, we have really 6 areas of product families that we're going to be focusing on. And I just want to give you just a quick word on each of these, and then I'll spend most of the talk describing the things that I think are most relevant to those of you working in Fab Labs. So for people who like to draw and sketch, we have tools in the Sketchbook family that are based on the same technology that professional artists and professional industrial designers use for graphics. 123D is a product we've talked about a little bit this week already, which is a new product that does design, 3D modeling primarily, for mechanical and other types of design. And it's basically repurposing a lot of the modeling technology that you see in products like Inventor and Revit and making it available in an easier-to-use, scaled-down version for non-engineers and people of all different levels of understanding of engineering and design, really allowing you to turn your ideas into reality. Pixlr is actually a company that we acquired a few months ago that is all about image editing and photo editing. And so we have a number of applications that are available for consumers to do photo editing. Home Styler deals with the home category. So people that want to do home design, to decorate your home, or to do interior design. And then Tinkerbox is really our first attempt at building a game really targeted at children, but it's a game that teaches you a little bit about physics and engineering. And so, the gaming aspects are really important, we think. It makes it a lot easier for people to learn if it's fun and exciting and interesting for them. And so this is really the first in a series of games that we'll be producing. And then we have the effects family, which is video and picture special effects, really just for fun, but to add some excitement and interest to some of your projects, making that technology available. So I mentioned the repurposing of technology involves price, scalability, access. It also involves platform. So one of the big things that we're focusing on with these products is making them available as online applications, so that you don't have, you don't get a package with 10 DVDs in the mail and you have to install a product, and it takes half of your day to install a product on your desktop or laptop. We want to make it more accessible. Also, there's a lot of movement towards mobile devices, tablets, phones, with Apple devices and Android devices in particular. We've seen a tremendous amount of uptake and engagement with those platforms. And so we're doing a lot more work in providing mobile applications. So I mentioned Sketchbook. Sketchbook is a whole family of products that scales from the iPhone and Android phone to iOS tablets and Android tablets. And then for Mac and Windows on the desktop, we have 2 lines of products, Sketchbook Pro and Sketchbook Designer. Sketchbook Designer is really kind of pushing into the professional area. Sketchbook Designer is a product that retails for about $500. Sketchbook Pro is in maybe the $30, $40 range, and our mobile products are either free or very low cost, like the $1.99 type of thing. So for Autodesk, this is really a new area for us to explore. And Sketchbook Mobile was really the first attempt for us to put an application into a mobile device and make it available for free or low cost. And it's been in our view, and the way our management looks at this, is that it's been very successful, we're really reaching a new audience and broadening, our really exposure throughout the market in different industries. I mentioned Pixlr. You can go to pixlr.com. It's we have an image editing capability that allows you to do a number of different things with just editing photos and other types of images. We have an application called Grabber that will take images off the internet and allow you to put them into the editing environment. We have a photo sharing or image sharing capability. And we have a new application we just released called Pixlr-O-Matic, which I'll show a short demonstration in a few minutes. But it's a very simple way to do easy edits to your photographs in just a few seconds. And it's just a good example of where we're headed in the way of making things very easy to use and understandable, so that you don't need to do a lot of training, you don't need to take a class, you don't need to read a book in order to use our applications. We need to make them very intuitive and very easy to learn. HomeStyler is another web application where you can design the layout of a room or the floor plan of your home, and then we give you content that is branded content from suppliers of things that you put in your home, furnishings or appliances, and then you basically drag them out of the content library, and then you lay out your home in a virtual world, and then you can do a high quality rendering, and this is all in a free application that's available at homestyler.com. So it's a thing that's really taking the interior design and some of the architectural technology that's available in other products that we offer and making it available at a very approachable level and a very affordable. In fact, it's basically a free application. Tinkerbox is a tool that really is our first game, and it has a physics engine. It allows people to explore the ideas of mechanisms. So I'll show an example of that. In fact, I have a little video here I'd like to show. So this is just a little example of how the application works. So you can see that we have different levels from very simple to more complex systems, and it's just a way to understand some very basic physics about putting different elements together and seeing how gravity affects. And you've got a challenge where a ball drops, you need to get it into the bucket. And then you get increasingly complex levels of sophistication with how you put the system together. And then there's an event mode where you can actually build your own design. You can put all the elements together, and then you can upload that and share that with others. So there's a lot of examples. We've got just over 1 million downloads of the application. This is a free application that today runs on the iPad. Okay. The next thing I'd like to talk about is 123D. So 123D will be a portfolio of applications, 3D modeling, 3D applications for creative consumers and digital makers from kids to adults to really explore and realize their ideas. Our goals with this whole program is really to teach people how to understand and to enjoy 3D. Because it's a big leap to go from 2D design to 3D design, to go from the 2D world to the 3D world. And we want people to have a fun and enjoyable experience. We want to see the immediate gratification to where they can get started with an application and do something interesting in a short period of time. We think providing content is very key to unleashing the creativity so that you don't have the problem of seeing a blank screen and not knowing how to get started with an application. It also allows you to share and then to be able to build on designs and projects that have been done by other people. Again, we want to make a very compelling and interesting experience in terms of the user interface and the way the product works. And a big part of the 123D is really the integration into the actual fabrication to make it very easy to go from the design world into the manufacturing world. a lot of the work that, and really the reason that I've been here this week and participating with Fab Lab is really to understand what our opportunities are for taking an application like 123D and directly connecting with the different fabrication tools, the NC machines, 3D rapid prototyping, laser cutting, those kind of machines, and finding really the best way to do that. And so we're very interested in working with some of you in the Fab organization to be able to do some early testing of our product and really give us the feedback to help us make sure that we're providing the tools in a way that they're productive for you and enabling. So 123D is a 3D modeling application. It's based on some of the same technology that's used in Autodesk Inventor. And it's a little different in the sense that it's not a history-based solid modeler. It is a solid modeler, but it's what we call a direct modeler, which makes it a lot easier to understand. It has features for building 3D capability, so you can do extrudes and revolves and put holes in the solid and add fillets and chamfers and things like that. It has an assembly mode, so here you can see we're putting parts together, and you can actually build constraints between the components, so you can have mates and flushes and different types of alignment, and be able to assemble a design. So it has individual part design, assembly design, and it has a basic capability for laying out a sheet to be able to produce a drawing of the results of your model. And what we're working on in the next couple of releases. We're putting out a release every month with this product. It's in beta right now. We released it in April. And the idea for the next couple of releases is to focus on the making aspect, or the integration of the design with the different fabrication machines that are available. But in addition to providing the tool, we feel that it's important that we provide the support around the tool for the tool to really be used and to be understood and accepted and to gain adoption. So that really means providing a destination website where you can go to get support, where you can go to get content. So we've got a lot of free content available at our website. The website for 123D is called 123dapp.com. And if you go there, you'll see this is the front page right here on the left. And it says create it, make it. There's a little bit of the screen's getting cropped here so you don't see everything. But there's content available. We also have kits for pre-built designs for fabrication, just very simple things to be able to make toys and things like that. The idea is that we'll be building a gallery, a public gallery, where people will be able to take their designs and upload them and then share them with the community. And that'll be coming online later this year. Right now the plan is the first release of the gallery being in October timeframe. And then to also provide a thriving place where you can get information about the application and about what people are doing. So learning and news, and then a whole community aspect that we're building out to make it easy to ask questions. This program is really one of the places where I've seen the most interaction between the development team within Autodesk and the users. So as I mentioned, we released the first beta version in April. So we've put out 3 releases since then. We've had 75,000 downloads to this point, which is pretty good for a desktop application. Today it runs on Windows platforms, and we're working on the Macintosh version as well. Just from some of our analytics, we've seen that people spend on average 1 hour in each session, which for a free application is really a long time. I mean, most web applications you'll see a few minutes. People spend a few minutes, up to 10, 15 minutes. So we feel like the people that are using it are very engaged. And with our community, we have this Get Satisfaction is a tool that's powering a community for exchange of ideas. And so people can report problems, they can ask questions, they can share their ideas, and then the development team, the product designers, the computer programmers working on the project, our quality assurance team, they all have been involved in responding to questions and asking questions, and it's really interesting to see the kind of engagement that we can get on. It's a lot less formal with the consumer products than it is with the more professional products, and that's exactly the kind of environment that we were trying to set up with these projects. 2 minutes, great. Another 123D product is something we call 123D Sculpt. And I'll just show another quick demo here. So this is something that we just released about 6 days ago. And it actually became the most downloaded iPad application in many countries and has gone to #1 in the entertainment category. So it's really getting a lot of adoption, about 800,000 downloads in 5 days. And this is a tool that's it's based on some of the concepts in some of our higher-end modeling tools for the media and entertainment industry. And what it does is it provides basic shapes and then gives you a very intuitive way to modify those shapes. So here you can see we give about 20 base models. These are 3D mesh models, and you can go in and change the model, and then you can really paint or do painting, graphic. You can draw on the models. You can actually take an image. So you could take a picture with your iPad, and then you can just rub it onto the model. So it's something it's actually very engaging. It's once you start using it, it's very hard to put down. I've wasted a lot of time playing around with images and models, but it's really fun, and it's a way to really introduce people to the concept of 3D modeling in a way that's very fun and entertaining. But at the same time, you learn about how you can manipulate a 3D model in a virtual way on a computer, and using the graphics to do some interesting things. So again, this is a free application. Today this runs on an iPad. We're working on Android versions and versions for Mac and Windows. And then this is another place where content is going to be important to be able to share and produce additional models that people can use as starting points for their design. I think a natural extension for this is to be able to output the model and go directly to, say, a 3D printer. So you could design a shape of some kind and then make whatever modifications you want to it and then actually print and get a physical representation of your model. Probably the fastest way to go from a design to the physical world. Okay, so with that, I guess just the whole concept of connecting digital to physical is a really important aspect of what we're trying to do, and so hopefully this gives you some ideas about what Autodesk is doing in the area of consumer products. And I'll be around, the rest of today and tomorrow if you'd like to. I have these applications running on my iPad, or we can talk about maybe answer any questions you have. So thank you.
Note that all the presentations will be online on the website after the meeting. So questions, comments for Chris about design tools? So the question is barriers to getting users to accept tools.
I think there's a number of different barriers. When you go from a complex, kind of a high-end design or engineering application that costs $1,000, $5,000, $10,000 or more, where there's training involved, you need to go to a training class or you need to read a book or that type of thing. I think if it's a discipline that you're getting your livelihood from, you're an interior designer or something, or you're an architect, or you're an aerospace designer, something like that, then it's reasonable to do that, and you want the power and you want the capabilities and you want to be able to really master a complex tool, and you'll put in the time. I think at the consumer level, people are really looking at being able to do something quickly. They don't need all the power of the more complex product. They don't have the money or the time to invest in developing the skills. And I think it's more important to get kind of the multidisciplinary aspect of it. So you don't spend all your time working on finite element modeling and structural analysis of your design. You maybe want a little bit of structural analysis tools that could help you, or something like that. But really, you want to be able to go from concept initial sketch or concept of a design into building the shape and the form of your design, a little bit of engineering that's necessary, and then get quickly to the point where you can fabricate. So it's a lot more, I think, learn by doing. And, the barriers are cost, the barriers are taking the tools to the level where they're easy enough to use and intuitive enough that you don't need to take a training class or you don't need to read a book, and you can pick them up. I mean, people like 123D Sculpt, the last thing that I demonstrated, people can, in about 2 or 3 minutes, they basically learn everything about the application. And the learning and the help is built right into the application. So those are the kind of things we need to do to overcome those kind of barriers. But it's really the time, cost, complexity. Those are really the main things I would say. And then there's also just the exposure. I mean, just making it so that people know that these tools are available. I mean, I would guess that very few of you even knew that we had a free 3D modeling mechanical design application available on our website, 3 months ago. I mean, I'm sure there's a few of you that have played around with it a little bit, but so really getting the word out is a big part of the barrier to that adoption of the tools as well. That's why I'm here, and that's why we're doing more things, on the internet and trying to integrate with the social networking and things like that to get the word out.
So you can take Chris's talk as a homework assignment. They're going to be working with the Fab Lab network to provide these tools, blow them out, get feedback. The homework assignment is to think about what should the tools do? How should they evolve? And the exciting collective challenge is the tools still assume that designing something and making something are separate steps. One of the directions we expect in the coming year is smushing them together, so there's a seamless transition from designing and making in both directions.
Absolutely.
Okay. With that, congratulations on, again, graduating from the hard session. We'll start after lunch with food and toys and things like that, and take a half an hour break now. Thanks to all the speakers.